Welcome back to the AS Chemistry lecture series. Today we're doing chapter 2, section 5, which is going to focus on the patterns in atomic and ionic radii across the periodic table. So we're going to look at both atomic radius and ionic radius and how these change both from left to right across a period and from top to bottom down a group. So let's get started. So the periodic pattern of atomic radius is what we're going to start with, because ionic radius is going to build off the atomic radius. Now, whenever we talk about the atomic radii, we're in essence talking about the size of the atom. Now, with the size of the atom, we need to talk about how we define that size, because like we discussed with quantum mechanical model back in honors chemistry, the atom is not actually something that is solid. It's not a sphere like we imagine it. It is something that we are going to have a variation as we go around the atom because of the sp, d, and f sublevels and orbitals and all the weird shapes that they have. So in order to define atomic radius, we use this definition. Atomic radius, or radii, which is the plural, is defined as half the distance between the nuclei of two covalently bonded atoms of the same type. Essentially, when we're talking about atomic radius, we'll have two atoms that are bonded together covalently. So let's say, for example, bromine. So we'll have an atom of bromine bonded to another atom of bromine covalently. Now, when we talk about the atomic radius, we define the size of this atom, or the atomic radius of this atom, as half the distance between the two covalently bonded atoms. So if this is our two atoms that are covalently bonded, and this is the nucleus in the middle of the atom, if we grab the distance from nucleus to nucleus and we divide it by half, so if this is the nucleus to nucleus distance, if we divide that by half, and I know this is not exactly half, but pardon my drawings, then that distance should be the radius of the atom. So this is R, and had I drawn this any better, this will be R, and they will be equal to each other. So we do this because there isn't an actual radius, right? We can't actually measure the distance from, for example, here to the edge of the atom, because this edge of the atom doesn't actually exist. It's not something that is solid. So instead, if we grab two identical atoms, like two atoms of bromine that are bonded to each other with a single bond, if we measure the distance between the nucleus and divide it by half, in theory, that should be the atomic radius of that atom, because the distance between them, if we go exactly halfway between them, that should be the frontier or the barrier between the two atoms. Now, this is not the only type of radius measurement. Now, this is what we call the atomic radius. But we can use similar ideas for the radius of ions in ionic compounds. We can use similar ideas for the radius of metals in metallics. Bonding, so in something like gold or silver purely, because those things don't covalently bond. Now, atomic radius is, however, defined as half the distance between covalently bonded atoms. If we were talking about something like metallic radius, that will be half the distance between two metallically bonded atoms, so on and so forth. So this is not the only type of radius measurement, but it gives us the best data when comparing elements across a period, because most of those elements are not be able to bond covalently in some way, shape, or form, or we'll be able to get those numbers from covalent compounds. Now, when talking about atomic radius trends in the periodic table, we're going to focus on two factors: nuclear charge and the number of energy levels. So this is going to be very similar to a conversation we had with ionization energy, and we are actually going to go more in depth into this in the next section, where we talk about every factor individually. Know that for the most part, anything that affects ionic ionization energy is going to affect atomic radius. The one where we obviously leave out of the conversation is the size of the atom, because when we're talking about atomic radius, we are talking about the size of the atom. So we focus on two things: the nuclear charge, or the charge within the nucleus of the atom, and the number of energy levels. So the atomic radius of the element is going to decrease across a period. And that's because the effective nuclear charge increases across a period. And again, if we go back to our basic idea of the atom. So let's get an atom here. So if we get an atom, try to make it as round as possible. That atom in the center has a positive charge. So let's call this, let's say, we'll start with maybe +3. If we have an atom with a +3 charge in its nucleus, and then we have a different atom, let's make it a different color, with a nuclear charge of +10. Oops. We have to realize that the amount of pull that atom has is going to be different, or that nucleus has is going to be different. Essentially, both of these nuclei are going to be attracting the, let me make that a little smaller, are going to be attracting the electrons that make up that atom. So we have the nucleus in the middle, and then electrons that are attracted towards that nucleus at the center. All of the different energy levels are going to be attracted towards that nucleus. So whether it's the first energy level, second, third, whatever, they're all going to be attracted to a nucleus. Well, if we have a +3 nuclear charge, that attraction is fairly weak because it's only +3 in its center. However, when we have a +10 charge, the attraction is much greater because we have essentially a much stronger magnet, a much stronger positive charge at the center than we do with the +3 nuclear charge. So essentially, if we have more protons, we have a higher positive charge, which has more attraction for the electrons on that outside layer. Because again, all of these atoms out here have electrons. Let's make these electrons in, let's say, green. So we have electrons out here that make up the electron cloud of the atom. Well, those electrons, being negative, are going to be attracted to the nucleus, but they're going to be attracted much more in a +10 nucleus than they are in a +3 nucleus. And if that's the only thing that we have to consider, then that means that an atom with a +10 nucleus is going to be much smaller than an atom with a +3 nucleus, because those electrons are going to be pulled into the center a lot more strongly than if you have a +3. So the higher the nuclear charge at the center, going back to our PowerPoint, the higher the nuclear charge at the center, the smaller the atomic radius is going to be. So again, the atomic radius of the elements decreases across a period, and that is because the effective nuclear charge is going to increase across a period. And we can see that with a periodic table and just looking at the atomic numbers. So if I bring up my periodic table here, across a period, so let's go across, let's say, period 2. So we go across period 2, the atomic numbers go from 3 to 4 to 5 to 6 to 7 to 8 to 9 to 10. So what we were comparing before is essentially comparing lithium to neon. As we go across this period, let me do it in a different color. So as we go across this period from lithium to neon, our proton number goes up as we go from left to right. And if our proton number goes up, so does the attraction of the electrons for that nucleus. And so lithium has a much smaller attraction of the electrons in the center, or the electrons on the outside to the nucleus, than neon does, which is a much bigger attraction. And so lithium is going to be much bigger than neon, which is going to be much smaller because of that internal attraction. So we say our atomic radius goes, let me use the arrow. Our atomic radius goes down from left to right because the proton number goes up, and so does the attraction to the nucleus. All right. And this is not happening in any, it's not just in period 2 or just in period 3. It's not happening across every period, mainly across the representative elements. Whenever we are doing this kind of trend, we often ignore the transition metals, because the transition metals are going to have a lot of exceptions in them. So we usually go only with the representative elements, which are the S block and the P block at the sides. And we kind of ignore these elements in the middle. And you'll see why in the next slide when I show you a visual representation of this. Now, you might be asking, well, that's nuclear charge. What about the number of energy levels? Well, across a period, the number of energy levels stays the same. From lithium to neon, the energy levels stay the same because we're still in energy level 2. Across energy level period 3, we're still in energy level 3. Across period 4, we're still in energy level 4. So the energy levels don't change when we're comparing elements in the same period. And that's something we need to keep into consideration. Do not use energy levels when comparing elements in the same period. What you do want to do is say that their number of energy levels is the same, because the outermost energy level is the same. So it stays constant. Now, when do we compare energy levels? We compare energy levels when we're comparing going down the group. Atomic radii is going to increase down a group, and that is simply because there are more energy levels. There are new energy levels as we go down the group. And that's very simple. We can take into consideration, for example, in group 1, as we go from period 1 all the way down to period 7, we have 1 energy level in period 1, 2 energy levels in period 2, 3 energy levels in period 3, so on and so forth. And that is going to change our number of our atomic radius if we change the energy levels. So if we go from hydrogen to lithium to sodium to potassium to rubidium, cesium, and then francium, essentially what's going to happen here is that we add levels. So if we have hydrogen, we have 1 energy level. And I did that very poorly. Let me use a circle function. If we have lithium, let me use a different color. If we have lithium, then we're going to have 2 energy levels around lithium. If we have then sodium, we're going to have, let me put this a little farther down. We're going to have 3 energy levels around sodium. If we have potassium, which is in period 4, again, let me put this farther down. Oh, let me use a different color. If we have potassium, which is going to be in period 4, we're going to have 4 energy levels around potassium. So 1, 2, 3, 4. Oh, that one's bad. And I mean, I'm not making them perfect, but you get the idea. The more energy levels we have around that nucleus, the larger these atoms are going to get. And so, as we go from energy level 1 to 2 to 3 to 4 to 5 with rubidium, 6 with cesium, and 7 with francium, these atoms are going to get larger and larger and larger. Now, do the charges of the nucleus increase? Yes. But it is overwhelmed or outperformed by the increase in energy levels. And that's something we need to keep in track. So if we're explaining the difference in size between, for example, lithium and potassium, we can say that the number of energy levels increases, which increases the atomic radius. The number of protons, or the proton charge, also increases, but it is outweighed by the number of energy levels. Outweighed being a classical word that we use in that scenario to say that, yes, that goes against what we would be looking at or what we're thinking, but it is actually not important. Oops. So, going back to this. So we have, if we're comparing elements in the same period, we say the atomic radius is going to decrease across the period, because the effective nuclear charge increases while the energy level stays the same. While if we're doing the atomic radius down a group, we say the atomic radius increases down a group because there's a new energy level in each group, and even though the proton number increases, it is outweighed by the new energy levels. So we kind of gotta make the comparison we talked about at the end of the year, where when you're comparing things, you say what is the same and what is different. And if there is something that counters what you're explaining, you don't just ignore it. You say it's there, but it is outweighed by the factors that you're using. So let's look at the next slide and we can explain that a little better. So we can see here, again, when we're doing this, we're kind of going to ignore the transition metals, because the transition metals provide a lot of exceptions that are not going to follow these rules. Same thing with the inner transition metals. We're just going to look at the representative elements. And we can see here how going across a period, so let's use pink for this, going across a period from left to right, we get that atomic radius decreases, both because energy levels stay the same and because proton number increases. So because the proton number goes up, but the number of energy levels stays the same, the atomic radius is going to decrease from left to right. And we can see that here as we look at from lithium to beryllium to boron all the way down to neon, how they get smaller and smaller and smaller. Same thing across period 2, same thing across period 3, same thing across period 4. Again, not taking into account these transition metals. So actually, let's do this with transition metals. Let's put a box around them too. So these are the parts that we're ignoring when we're talking about these trends. And we can see how if you're going to jump over this, it was bigger, smaller, and then it just keeps getting smaller from left to right. Now, the other one we got to look at is the group. As we go down the group, well, it's in yellow. So we look down the group, we can see it very clear as day with group 1. The ionic atomic radius gets larger. So down group 1, atomic radius gets larger or increases, which we need to use those proper terms. Atomic radius increases because energy levels go up. So we have more energy levels. Proton number goes up, but is outweighed by the energy levels. So you need to make sure you kind of hit every point there. And obviously the one that's not on here, but it's part of that thought process, is the attraction of the nucleus. We discussed shielding in an earlier section. The shielding is what makes those electrons in the inside layers kind of allow for less attraction to hit the outside electrons. So the fact that we have more energy levels, that's related to shielding. The more energy levels we have, the more shielding there is, the less attraction the other electrons have, and so they get bigger. Nope. So make sure that you hit these points as well as the magnetic attraction when you're talking about these in an answer choice. Also, it will depend on how many points that question has associated with it. All right. And we can see this, and this is something that you're not used to, but in AS chemistry, you're going to have to start addressing or being able to address graphical data and charts. So here we have graphical data that is associated with, I believe this is period 3 of the periodic table. So we have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And we have here both the tabulated data in a chart and the graphical data in a graph of those elements. So here we have sodium's atomic radius is 0.157 nanometers, magnesium 0.136, aluminum 0.125, silicon 0.117, phosphorus 0.110, sulfur 0.104, and chlorine 0.099. So we can see here visually in the graph that as we go across the period, the atomic radius decreases. And they might give you this data and just something as simple as explain why. They could also give you this data and ask you to explain or to address which one of these elements is which, if they only tell you this is group 2, but they don't tell you the actual elements or the atomic numbers. So there's a few things that they could ask you just by showing you this data. Again, we have to realize that here we're going across a period, which means a couple things. It means number of protons is going up, which means there is more attraction of electrons to nucleus. Because remember, if the number of protons goes up, then there is more attraction of the electrons to the nucleus. Ooh, what did I just do? Oh no. Oh, well, there goes that. Let's redo that. So again, number 1, number of protons goes up across period. So again, in this case, we do need to be specific because they give us a specific data from sodium to argon, or to chlorine here because they don't give us data for argon. Number 2, attraction of those electrons is going to increase for the nucleus. And that's really what's pulling this atom smaller. That's why the atomic radius is smaller, because the attraction of the electrons in the outside electron cloud to the nucleus in the center. So that's going to increase, and that's going to decrease the atomic radius for that for those elements from sodium to chlorine. And then finally, you always need to mention the number of energy levels remains the same. Or you can say the shielding remains the same. So this is just a basic explanation that we will give for this phenomenon of the atomic radius going down from sodium to chlorine. The number of protons in the elements goes down across the period from sodium to chlorine. Goes up, not down. The attraction of the electrons for the nucleus is therefore going to increase from sodium to chlorine because of that. And then that causes the decrease in the atomic radius that we see because those electrons are more attracted to the nucleus. Finalizing it with just mentioning the fact that the number of energy levels or the shielding is going to remain the same as this happens. And so that doesn't affect our atomic radius. But be ready to look at data like this because they will give you a lot of visual data such as this in the AICE exam, where you have to just look at it and kind of talk about the theory that you learned based on that graph. you need to be able to put 2 and 2 together. These cannot be separate ideas in your head. You should be able to look at this data and say, okay, this is data about atomic radius. It's decreasing because I'm going across period 3, which is sodium to magnesium. Sodium to chlorine and argon. And so being able to explain that with what you learn about those things. That's going to be a very important skill for you. Now that we talked about atomic radius, let's talk about ionic radius. An ionic radius basically has the same ideas, are the same basis as atomic radius. So ionic radius refers to the radius of an ion of the element. So we're still looking at the same elements in theory, but we're looking at their ions, meaning once they have either gained electrons if they are anions, or lost electrons if they are cations. The ionic radius of a cation, specifically, is going to be smaller than that of the atoms and decrease down a period. So this is very important, this first part, because the decreasing down a period, as we go from left to right, that's just what atomic radius does, right? So we have to be aware that the basic trend of ionic radius is going to be essentially tied to that of atomic radius, because a larger atom gives you a larger ion. It's as simple. The idea here is realizing what happens when those atoms either gain or lose electrons. So the ionic radius of a cation is smaller. Let's dissect that part first. Let's put this in yellow. The ionic radius, the ionic radius of cation is smaller than that of the atom that it came from. What this essentially means is that if we have something like sodium plus is going to be smaller than sodium atoms that are neutral. And this is because we have lost usually energy levels, especially when we're talking about representative elements. And they have a higher effective nuclear charge because of that. So let's look at this in a more visual manner. So if we have the sodium atom, oh, that's very big. Now the sodium atom, in the sodium atom we have 3 layers. 1, 2, again, that's not the most centered thing, but 2, 3, and then in the center we have our nucleus. Positive charge here. So let's talk about what happens as we make an ion. If this is sodium, I'll go back to, if this is sodium here, the sodium atom has 11 electrons. We'll draw those here in blue. We have 2 in the energy level 1. We have 8 in energy level 2. And we have 1 in energy level 3. So this is the size of the sodium atom. When that gets copied over and creates the sodium ion, there's in white. When that gets changed to produce the sodium ion, Na+, the sodium ion now has 10 electrons, as opposed to the 11 electrons that the atom of sodium had. Well, what does that mean for our sodium atom? Well, the sodium ion, we're essentially going to be getting rid of a whole layer. So when we go from Na to Na+, using the same drawing, we're getting rid of 1 electron. Well, the 1 electron is going to come from the outermost energy level. So this electron out here in energy level 3 is gone. But that leaves that energy level empty. So it's not there anymore. So what's going to happen is, if we look at the difference, this is the sodium atom. When we create the sodium ion, get rid of this electron, we're getting rid of a whole energy level, which makes a whole ion much smaller. So this is no longer the sodium atom. This is now the sodium ion, which has lost that 1 outside energy level. And so it becomes smaller. So by virtue, cations are going to be smaller than their parent atom. And this is why, because most of them are going to get rid of an energy level. Now that's pretty straightforward. So again, this is because they have lost an energy level and have a higher effective nuclear charge that across the period. Again, why does that mean? That just simply means that because we have lost an energy level, we have lost shielding, and so the effective nuclear charge is larger. We're going to have more attraction of those electrons for the center because we have lost a whole level of shielding. On the other hand, ionic radii of anions is going to be larger than that of the parent. And now that reasoning is pretty straightforward, right? Because the ionic radii of an anion is larger than that of the atom. That's just the opposite of the cation. But the reason why is a little more complex. This is because they have gained electrons, which does not give them more energy levels, but what it does do is that it increases repulsion. So with the same number of protons but increased electrons, we're increasing repulsion, which is just going to push the whole ion farther out. So again, let's look at that in a more visual manner, right? Because I can tell you this, the ionic radius of anions, negative ions, are larger than that of the atom, and that's because of increased repulsion. But what does that actually mean? So let's look at an ion of, let's say, sulfur. Let me pull up. So if we draw sulfur, we're going to have our positive ion at the center, or sorry, our positive charge of the nucleus at the center. And then we're going to have our energy levels. So sulfur has 3 energy levels. 1, 2, 3. Now, neutral sulfur, just S, on the periodic table has, and let me pull up the periodic table. I'll be able to do that. Sulfur, neutral sulfur on the periodic table has 16 electrons on it. So those 16 electrons are going to look like this. We're going to have 2 in the first energy level. 1, 2. 8 in the second. 3, 4, 5, 6, 7, 8, 9, 10. And then we're going to have 6 electrons in the third energy level. 1, 2, 3, 4, 5, 6. So what happens here, what if we want to make sulfur 2+? If we want to, 2-. Sulfur 2- goes from having 16 electrons to then adding 2, meaning we have 18 electrons. When I add these 18 electrons, sulfur originally has a nuclear charge of 16+, because it has 16 electrons. When I add the 2 electrons on the outside energy level, I'm not adding any energy levels. So that's not why this ion gets larger as it becomes sulfur 2-. What I do, though, however, have when I add 2 more electrons is that these 2 electrons are going to add more repulsion between the outside and inside layers. There was already a repulsion on the outside layer from 6 different electrons that was there before. And that's what kept the atomic size of sulfur what it was. When I add these 2 electrons, I'm adding more repulsion for those inside layers and more repulsion between the electrons in that outside layer. All this repulsion causes this +16 charge in the center of the atom to mean less, to be kind of downplayed by the repulsion that I have added. So what does that do? Whenever I add that repulsion, this whole outside layer gets pushed even further out. So instead of that inside layer being there, I'm going to erase it. This outside layer now gets pushed even farther out by all this added, erased too much, by all this added repulsion that I have added from my 2 extra electrons. So where that outside layer before was here, it's now farther out because of the added repulsion. So those electrons that I had before had 6 electrons naturally. Now I've added 2 extra electrons from that 2 minus charge on the ion of sulfur. And that added so much added repulsion between these electrons that it made the ion grow larger. So the anions, because of this, are larger than their parent atom. The S2 minus ion is larger than the S atom because of the added repulsion from having those extra electrons on that outside layer. We haven't added any protons, so there's no added attraction. There's only added repulsion, and so that makes the ion grow bigger. All right? So that's what we mean by when we say, let's go back to this, that the ionic radius of the anion is larger than that of the atom because of the added repulsion and the same number of protons. Positive charges don't increase, but negatives do, which causes more repulsion between the electrons. And this is going to decrease as we go down the period. Again, I haven't mentioned this a lot. Why does it decrease as we go down the period? That's simple. It decreases down the period because as we go down the period, those energy levels are closer and closer together. And so because they're closer and closer together, the amount by which that anion grows is less and less and less. But that's not what we want to focus on. The ionic radius of the anions is what we want to focus on. And the fact that as we go from the atom to the ion, that ion is going to get larger. Now, so ionic radii is going to increase down a group for all ions, and that's simply because of the added energy levels. Simply enough put, because atomic radius increases down a group, so does ionic radius, because larger atoms make larger ions. Ionic radii decreases across a period, and this is where it becomes important for you to know these 2 prior points, because as we reach the metalloid ladder, we have a shift. So it's not a decrease across a period, but then when we get to a metalloid ladder, we're shifting from making cations to making anions. And I'm going to show you a graphic in a few seconds. That's why I make that a little more visual. But we're going from making cations to making anions. So we're going to decrease across the period, but there is a large increase as we cross the metalloid ladder. The decrease is due to the increasing number of protons in the nucleus across a period. So again, why do ionic radii decrease across a period? Simple, because atomic radius decreases down across a period. That's just what they do, and it's going to reflect in the ions, because smaller atoms make smaller ions. However, you have to now realize that there's going to be a jump when you get to a metalloid ladder, because we go from the metals which are creating cations to the non-metals which are creating anions. So let's look at that. And again, graphical data, because it's very important. As we go from the sodium ion, which is Na+, to magnesium 2+, to aluminum 3+, to silicon 4+, we have a general decrease. So from, and we'll make this a little bigger. So here, we have a decrease in ionic radii because we have proton number increasing. So we have an increase in the number of protons, same energy level, and so the ionic radius is going to decrease as we go. However, there is a big jump from silicon to phosphorus. And again, why is there a big jump? Look at phosphorus, look at silicon. We go from cations, we go from positive cations to negative anions. So we're going from positive to negative. What did we say about cations? They're smaller than the parent. Anions are smaller than the atom. Anions are bigger than the atom. And that's why this jumps, because these are smaller than the parent atom. These are bigger than the parent atom. There's a division between them. So from silicon to phosphorus, or from any time when you cross the metalloid ladder, we're going to have this large increase in the ionic radius. But then once we get to the other side, again, we start decreasing again. Why? Because of the same reason we had before. Because there's a decrease in in the number of protons, or an increase in the number of protons, which increases the attraction for the nucleus. So it's very much like our, I'll go back for a second here. It's very much like our atomic radius trend, but there's now an increase in the middle between silicon and phosphorus, or between the metalloid and the non-metal, that is caused by the difference between anions and cations being created. All right, so you need to be able to address that, and address the difference between ionic radius and atomic radius as we talk about this. All right, that is it for section 5 of chapter 2. See you again to discuss chapters 2, section 6 in the next video.